So we finished our conversation on Thursday we concluded it with the discussion about the carbon dioxide transport. Figured it all out. And now the question is how our nervous system controls the respiratory function. So basically, there are several things that are involved. There are nervous controls that involve the higher brain centers. By higher brain centers, we mean, cortical controls. We can hold our breath. Of course, there are metabolic control mechanisms which involve elevated respiratory rates when, say, we experience metabolic acidosis and so on and so forth. And now, the parts of the central nervous system that are directly involved in autonomic control, and that's what I want to say, autonomic control of respiratory function, are medulla and pons. Now, when I say autonomic, I mean that, look, you don't think about breathing. This activity is autonomic. You don't think, I need to inhale, I need to exhale, right? So, these activities are controlled by medulla and pons. In medulla, there are two groups of neurons, the ventral and the dorsal respiratory groups. So the ventral respiratory group controls the normal breathing rate, sets so-called eupnea. Okay, eupnea, eu means like true, pnea, breathing. Controls normal respiration, sets the normal resting breathing rate, about 12 to 15 breaths per minute. Now, dorsal respiratory group does not interact directly with the respiratory muscle. If we would like to draw it, it would be something like that. So ventral respiratory group sends the signals to muscles. Okay? Diaphragm and intercostal muscles. And then you have dorsal respiratory group that produces certain nervous patterns to send them to the ventral respiratory group. Modify the activity of the ventral respiratory group depends on the peripheral pH, right? Stretch of the lungs, changes in the blood chemistry. Does that make sense? So it doesn't signal to the muscles itself. It communicates the ventral respiratory group. Now what about the pontine centers? Pontine centers mainly, okay, are responsible for the smooth transition between the inspiration and expiration. Here you can see the pontine respiratory center communicating directly to the dorsal respiratory group and ventral respiratory group. Now you can see that there's only one set of neurons that actually sends the output to the muscles, ventral. Okay? Others communicate down to it. Basically, neurons in the pons are involved in sort of modified respiratory movements like speaking, singing, changing the respiratory pattern during the exercise. Interesting thing is that we're still not exactly sure what is the mechanism of setting the actual eupnic respiratory rate, normal respiratory rate. One idea is that it might be pacemaker cells, Okay, but since the transition is fairly smooth and not very much dependent on both aspects of autonomic system, I mean sympathetic, parasympathetic, most likely you have two sets of pacemakers that reciprocally inhibit each other. Does that make sense? So when one takes over, say set 1 takes over by inhibiting set 2. Set 2 takes over by inhibiting set 1. That's what we mean when we say reciprocally. We clear? So sort of a take-home message, we have 3 groups of neurons: ventral, dorsal, and pontine. And ventral sets a normal rhythm, dorsal modifies this rhythm, and pontine smoothes out the transition between 2 stages of ventilation. Are we clear? Awesome. What influences the breathing rate and breathing depth? The most important factors of blood chemistry, basically. Okay. Well, yes. Normally, I'm not taking into account, for now, I'm not taking into account the situation when you exercise, because technically it's not normal. Correct? So the main factor, levels of carbon dioxide, hydrogen, and oxygen. And these levels are sensed by the chemoreceptors. And first, we're going to talk about the respiratory adaptations to the changes in blood chemistry. So first and foremost, the most important factor that regulates the breathing rate is the partial pressure of carbon dioxide in the blood. We're clear? The partial pressure of carbon dioxide in the blood increases. How does it change the blood pH? It decreases the pH. Blood becomes more acidic. What is the problem with acidification of the brain? Which effect does it have on neuronal activity? It shuts it down. Yep. Acidosis decreases neuronal activity and in the extreme case may lead to coma. So brain tries to restore the blood pH, bring the carbon dioxide concentration in the blood back to normal. Okay? So these elevated levels of carbon dioxide are sensed by both central and peripheral chemoreceptors. Signals from those chemoreceptors reach respiratory centers in the medulla, mainly dorsal respiratory group, which immediately modifies the pattern produced by the ventral respiratory group, which immediately sends the contractile pattern, new contractile pattern, to the intercostals and the diaphragm. These muscles start to contract more frequently with a higher amplitude of contraction, which increases both depth and the rate of breathing. When we breathe faster and deeper, we expel more carbon dioxide. Does it make sense? As we expel more carbon dioxide, its concentration in the blood decreases. Correct? And the pH of the blood increases, goes back to normal. Essentially, if you think about it, these factors, both these factors, they do contribute fairly equally to the breathing rate and the breathing depth. I'm talking about CO2, pressure in the blood, and pH. Okay. pH is maybe slightly different. Now, what can cause elevated, what normally produces CO2? What produces CO2? tissues. Right? Respiration, it's a product of respiration, cellular respiration. So basically, failure to expire CO2 normally will lead to the increased CO2 concentration in the blood due to normal cellular process, oxidative respiration. Does that make sense? Now, I want to ask you a little question here. Imagine brain. Imagine that concentration of CO2 in the brain increases, in the brain tissue or in the blood that goes through the brain, which means basically in the brain parenchyma. CO2 concentration goes up. How does it affect the diameter of cerebral blood vessels? Higher CO2 leads to vasodilation. Are we clear about it? Okay? Because brain tries to get rid of that CO2 as fast as it can. Good? Now, what happens that if you are breathing normally and then you suddenly decide to hyperventilate? What happens to the CO2 levels in the blood? They decrease immediately because you remove them, so-called hypocapnia. Now, if elevated CO2 levels cause vasodilation, then reduced CO2 levels will cause vasoconstriction. Vasoconstriction of cerebral vessels will lead to the decrease in the blood supply to the brain. How does it affect neuronal activities? Decreases. Neurons basically, they do not receive enough nutrients and oxygen. And what person does? Huh? What? No. I'm the living proof that no. Person doesn't die. What person does when cerebral vessels constrict? First, passes out, yeah. I was in the 4th grade, I think. I had this wonderful, don't do it at home, kids, thing going on. You do 20 squats, okay? And then you breathe really, really hard. Like you hyperventilate for about 5-10 seconds. And then your friend pushes in your chest. So hyperventilation decreases, constricts the cerebral blood vessels, and additionally that decreases blood flow to the brain even better. And you pass out. That was fun. But I didn't realize there was a concrete thing behind me, so I fell my head right in that concrete thing. Which actually proves that at that age, the head is the entire bone. I didn't have even a mere concussion. I just had my skin stitched and that's it. It was fun. But again, don't do it. Or if you do it, like, have something soft to fall on. Anyway, now if the CO2 concentration becomes abnormally low in the blood, okay, this may lead to the condition known as apnea. When blood vessels in the brain constrict so much, the person stops to breathe. It's not going to kill you, but it's going to wake you up. Because it is usually happening in the sleep. One condition with which apnea is associated greatly is obesity. Another condition, well, not condition, but what is outcome? You wake up in absolutely terrible shape. You don't sleep well. And it's sort of like, I'm kind of maybe stretching it a little bit, but it's sort of a self-promoting situation, because it was shown on multiple occasions that the sleep deprivation leads to overeating. Overeating leads to obesity. Obesity leads to apnea. Apnea leads to the sleep deprivation. So in the long-term run, it kind of sucks. Okay, apnea can be diagnosed. There are sleep labs. So if you have trouble sleeping, the specialist in the sleep lab will determine what's going on with you and will recommend treatment. Okay. Questions? Do you understand the CO2 part of regulation? Good. I'm going to talk about pH first. So pH, even if you have normal CO2 and oxygen levels in the blood, elevated concentration of hydrogen ions, meaning low pH, leads to increased respiratory rate and depth. Okay? So pH, it probably should be, I don't know what I wanted to say here, but just either just get rid of it entirely, but respiratory system tries to adjust pH. Do you understand? Now, what is more common, do you think? Metabolic acidosis or metabolic alkalosis? What is more common? Your blood pH drops or your blood pH increases? What did you hear more? Acidosis or alkalosis? Acidosis, yeah. I can't really think from top of my head about a condition which would produce like metabolic alkalosis of a considerable level. Acidosis, of course, lack of insulin or kidney failure. Okay? When kidneys fail to regulate blood pH decreases. The compensatory response comes from the lungs. Now, you may ask, wait. Why lungs compensate for malfunction of kidneys? The answer is in the question. Because if kidneys don't work properly, they cannot compensate for their own fault. Does that make sense? So that is why when there is a kidney failure or any underlying metabolic condition which constantly produces hydrogen ions, your respiratory rate and depth will increase right away. Does that make sense? Okay? Are we clear about it? So low pH increases respiratory rate and depth. What about oxygen? Well, oxygen is pretty much, it's logical, right? If oxygen levels go down, then your respiratory rate and your depth, they will go up. Because you have not a lot of oxygen in the blood, then you will start to breathe harder. Okay? Now, here's the deal. The most powerful mechanism to control respiratory rate and depth is CO2 levels. Does that make sense? That's the most critical regulator of your respiration. Why not oxygen? Well, if oxygen is too low, it's also bad. What is so peculiar about oxygen levels in the blood? Do they ever go to zero? No. Why? The venous reservoir. Yep. The venous reserve. Oxygen is bound to hemoglobin. Even after the unloading in tissues, you have plenty of oxygen. So unless the partial pressure goes really, really down, oxygen does not play a tremendous role. Does that make sense? I'm still trying to recall the mechanism that can promote drowning when you hyperventilate before diving. Now, think what can happen. No, I wouldn't take it right away. I need to look it up. There is a mechanism that actually suggests that if you hyperventilate, you know how people breathe really hard before they try to swim underwater as far as they can. There is a mechanism that suggests you have a higher chance to drown if you hyperventilate than if you not hyperventilate. Because instead of increasing oxygen concentration in the blood, you cannot do it. You hyperventilate, oxygen concentration, saturation of hemoglobin doesn't change that much, right? All you do is you decrease CO2. Okay? So basically, yeah, you do constrict the blood vessels in the brain. Well, hopefully it doesn't lead to anything, but you start swimming, and by the time the concentrations of CO2 reach the critical level, your concentrations of oxygen may also reach critical level, but in, the other way around. And it may be too late for you to try and, go up. Does that make sense? So basically, in terms of CO2 controlling breathing, we can voluntarily hold the breath. Can we? Can we suffocate ourselves if we're not underwater? No, I'm not saying like this, suffocate. Like if we hold our breath, can we suffocate ourselves? No. Because we will, at some point, CO2, the signal from peripheral chemoreceptors, these signals, they will override signals from the brain. Does that make sense? So we will take a breath anyway. That's why people drown. Now, speaking of the higher brain centers, there are some respiratory patterns that are not really voluntary, but they involve visceral respiratory responses. Say when we inhale when it's painful. Okay? Gasping for air when it's painful. But probably the most interesting cortical controls. So yes, we do have the ability to hold our breath. But more importantly, we have the ability to control breathing rate when we exercise, independently of the metabolic parameters. Before we discuss it, a few things. So irritant receptors in the respiratory passages and in the lung stimulate cough and sneeze. That's fairly straightforward, which is dislodge whatever is in there. Now that is a really interesting reflex. It's called Brewer reflex. So basically the question that we may ask is, can we inflate our lungs to the degree that they explode? Can we, have you ever seen the kid who took a gigantic a rubber, basically, a rubber bag, not the regular balloon, like rubber bag, inflated and exploded it? Yeah, so some people can produce enough pressure in expiration movement to explode like balloons and stuff like that. But the question is, can we produce enough pressure in the inspiration to overstretch and essentially rupture our own lungs? The answer is no. The reason for it is this Brewer reflex. What happens is, when lungs are stretched, the mechanical receptors in the lung stroma sense the stretch. And at a certain threshold, when stretch reaches a certain level, they send the signal to the medulla oblongata to stop inspiring and start expiring. Making sense? Basically protective negative feedback. Now, exercise thing. I'm trying to think how to. Metabolic parameters of your blood remain largely unaltered during exercise. Let this statement sink in. It means that if you would measure hemoglobin saturation during exercise and during resting state, they will be practically the same. If you would measure concentration of CO2 in the blood during exercise and during resting state, they will be practically the same. Even blood pH would be practically the same, which sounds absolutely counterintuitive, because when we exercise, what happens to the muscle metabolism? It dramatically increases, right? Which means muscles start to consume much more oxygen, correct? Produce much more CO2, and in some cases even produce lactic acid. So technically, what we should see, we should see low oxygen concentration, high CO2 concentration, and low pH. We see nothing of this. The reason for it is respiration. Turns out that when we start exercising, our breathing rate increases practically immediately. Think about this. You go work out. You start breathing hard right away. Try to maintain your normal breathing rate, your tidal, like resting breathing, if you're running or lifting or doing whatever, things like that. It's really impossible. It's physically impossible. However, I'm trying to kind of how to explain it. Well, think about this. All these changes that we just mentioned, elevated CO2, decreased oxygen, decreased pH, all these changes can happen only if the respiration stays at the resting level while metabolism kicks up. Does that make sense? What happens is, the second you start exercising, your respiration increases. Okay? Now, what increases it? You know that you're going to exercise. You know you're going to run. That sense, like, that's cortical signals. Okay? Second, when you start running, lifting, doing whatever exercise you do, your motor cortex produces output to the muscles. That output simultaneously stimulates the respiratory center. Okay? And finally, proprioceptors in the muscles and the joints, when they sense the increased tension or increased stretch or motion in the joints, they will send the signals to the medulla to increase respiratory activity. That makes sense. Just think about this. When you stop exercising, your breathing rate subsides very fast. Importantly, it doesn't decline, like your say you're running, your breathing rate, I don't know what, 40, 50 a minute, okay? You stop, it doesn't go down to 12 right away, right next second. The reason for it, although you stopped, there is increased metabolic activity in the muscles, okay? Basically, due to the oxygen deficit, it's post-exercise oxygen consumption, okay? So that elevated post-exercise oxygen consumption in muscles will still produce higher CO2 levels and lower pH. So your lungs will keep getting rid of that CO2 for some time after the exercise. As muscle metabolic activity decreases, your breathing rate decreases gradually. Okay? It increases almost immediately, it decreases gradually. Now, basically, it is practically impossible to achieve a mismatch between respiratory capacity and the requirement for oxygen delivery to the blood. Let me draw it here on the slide. What I'm trying to say is, this is alveolus, and this is capillary. Okay, so that's external respiration. In exercise or in the resting state, external respiration will be fine. All carbon dioxide that needs to be exhaled will be exhaled. All oxygen that needs to be delivered will be delivered. Okay? In tissues, in terms of the transport and delivery, it's not lungs anymore. Does it make sense? That's where the culprit is, the tissues. When you exercise, skeletal muscles contract, squeeze blood vessels, reduce blood flow to the muscles, forcing them to work in anaerobic conditions. So they start to ferment, they start to produce lactic acid. Does it make sense? That's number one. Action of the muscles. Number two, your cardiac output has limits. So if cardiac output doesn't match to the needs of the muscles in it, it may be the case. Okay? Especially in high intensity, short-term exercises. If cardiac output doesn't match the muscle needs, then amount of oxygen that is delivered to the muscles is insufficient, and muscles have to switch to fermentation as well. So you can see that those anaerobic conditions at which your muscles have to function, they do not stem from your poor lung capacities, poor respiratory capacities. They stem from either mismatch between the tissue requirements and the transport, cardiac output mismatch. Do that make sense here? That's one important thing. Don't blame your lungs. Okay. Now, what about adaptation to altitudes? Did you ever go to fairly high? I'm talking about the altitude. Just to specify. Had an experience with adaptation? How does it feel the first day? Oh yeah. Well, I went for 5 days. Elevation was about 8,000 feet. It's pretty interesting experience. But you adapt eventually. So first day, jogging in the morning in the first day was an absolute nightmare. And then it became a little better, not dramatically, but a little better. At least I knew what to expect. What you can expect. When you go up in the mountains, the concentration of oxygen, partial pressure of oxygen in the atmosphere decreases. Therefore, partial pressure of oxygen in your lungs also decreases. So hemoglobin saturation decreases. And that means that there's not enough oxygen that is delivered to the brain. There's brain hypoxia. And how brain tries to compensate for it. If there's not enough oxygen coming to the brain, what happens to the blood vessels? Huh? Not enough oxygen. They will do what? Think about it. Not enough oxygen reaches the brain with the blood. How would brain vessels compensate for it? Dilate. When they dilate, and they dilate when they quote-unquote not supposed to, so that elevated blood flow to the brain may result in a cerebral edema. Same is going to happen in the lungs. The blood flow will be increased to pick up as much oxygen as possible, which may lead to pulmonary edema. So it has to be... Now, what I'm saying is you're not going to die if you travel to Colorado. Okay, don't get me wrong. If you will try to go to the last base camp on Mount Everest, which is something like 18,000 feet, or like right away, like fly from here to Kathmandu and then go to that last base camp, good luck with that. they will ship you back in a coffin. Okay? No, seriously, you will die. So when people climb really high mountains, they have to acclimatize. It takes months. As far as I know, you can order a trip to Everest, like it's a tourist thing. It takes like 2 months. So you can fly, you have to go through the base camps, you have to adjust to everything, and yeah, eventually as a group you will be up there. It's a couple thousands dollars, something, 20,000, 30,000 bucks. Yeah, that's it. But you have to adapt to that change in oxygen concentration, and at the elevations about like 6,000 meters and higher, people who are not specifically trained for it, they have to carry actually oxygen tanks because it's just not enough oxygen for the normal breathing. Now, what acclimatization involves? First of all, chemoreceptors become more sensitive to carbon dioxide. So they start to learn to properly respond to CO2 concentrations in the blood in the situation when oxygen is low. Okay? It directly increases minute ventilation. Okay? You just start breathing faster, much faster. Okay? Now that is short term. Those adaptations, chemoreceptor adaptations, and minute ventilation adaptations, they are short term. They happen almost immediately. Again, based on my personal experience, you step out of the plane and you just start breathing faster. There's no other way. Okay? Long-term adaptation, of course, is production of erythropoietin in the kidneys and elevated levels of red blood cells. Okay? To kind of give you a perspective on climbing the tallest mountain in the world, there's a book. There's a guy called Reinhold Meissner. I don't really know if he's alive or not. He used to be. He's the first person in the world who climbed on all mountains taller than 8,000 meters. Something, 25,000 feet. So he was the first guy to do that. And he wrote a book called Crystal Horizon. It's utterly boring, really, because, well, for those who don't do mountain climbing and all that kind of stuff, it wasn't fascinating for me at all. But he had a story about he was the first person in the world to climb Mount Everest by himself. Okay. By himself, of course, we're not talking that he's standing like at the ocean level somewhere in India and then takes a staff and goes with his staff all the way up to the Mount Everest for like 3 years, basically. No, it means that he ends up with his friends and family at the last base camp. But from that base camp to the peak, he's alone. And he can carry only that much. So he did have some, enclosure, something like a tent, some food, and a smaller oxygen tank. So he made it all the way up there. And it was his own writing, so he wrote it, he remembers. And then he says, well, I'm on top, I could barely feel anything. He's half passed out because of the oxygen deprivation and lack of adaptation to that. Think about this. People who do the parachute jumping thing at this elevation, they jump with oxygen mask. That's high altitude. That's extreme jumping. He's there climbing. He's not flying in the air. He's climbing the mountain. So he ends up on the peak. He's all happy as he can be because he can barely understand what's going on. And then he starts going down. And then he doesn't remember anything. So basically what happened, he lost conscious on the way down because of exhaustion, physical exhaustion mostly, oxygen deprivation. and he passed out on Mount Everest, like in the snow. His wife, who according to him was rather small, woman, I think she was Japanese, like 120, 130 pound woman, she went out looking for him because he was supposed to be there, but he wasn't. And she found him in the snow. Now, I saw a photo of Meissner. He's like 6 foot guy, like guy. Not too huge, not too small, just 6 foot athletic guy. His wife, when she found him, she picked him up on the shoulder and carried him back to the base camp. So he lost like half of his body weight. He was emaciated to like a little extent. He recovered eventually. Why I'm saying I don't know if he's alive, those people, they die pretty frequently because of, mountains and all. But again, it shows you the extreme which our respiratory system can withstand. Sorry, now, the diseases. Chronic obstructive pulmonary disease. Now, I want to make very clear the difference, remind you about the difference between the obstructive and the restrictive diseases. Or, should I say, should you remind me, what is the obstructive disease? What happens in the obstructive disease? Not the vessels. Well, yeah, the passages. Perfect. Something's blocking respiratory passages. It can be, so obstructs them, right? They can be constricted, asthma. They can be blocked by mucus. Does that make sense? Okay. Now, emphysema exemplifies practically both, because in emphysema, there is an inflammation of bronchi that leads to the obstruction. But emphysema exemplifies also a restrictive disease. What does that mean? Yeah, basically the vital capacity and total lung capacity, they go down. Lungs are functionally impaired. Does that make sense? Okay? So here on the picture on the left, it shows a chronic bronchitis case. Somebody smokes or somebody is exposed to the pollutants, it leads to the constant inflammation of the respiratory passages. Constant inflammation leads to accumulation of mucus. Mucus leads to the obstruction of the airways and hypoventilation, hypoxemia. Okay? That makes sense. This is because, air cannot get in the lungs. In emphysema, alveoli start to break down. Now, what is better in terms of the gas exchange? To have 50 tiny alveoli or one big alveolus? 50 tiny. Because if you would calculate the surface to volume ratio for 50 tiny alveoli, the ratio of surface to the volume will be much higher. Which means, say, if you have 51 cubic micrometer alveoli, the surface of that respiratory membrane will be much higher, so we can put it like this. 50 by 1 cubic micrometer alveoli, surface of this will be more than surface of 1 alveolus with a volume of 50 cubic micrometers. Does that make sense? So which makes it the bigger alveoli, surprisingly, make the gas exchange less effective. which leads to, again, hypoxemia, but the reason is different. All the air gets in the lungs, it's all fine. Does that make sense? Now, the main cause of these diseases, of course, is smoking and air pollution. By the way, in emphysema, people will try to inhale more because lungs cannot, external respiration is impaired, so not all air that's in the lungs is transported, not all oxygen from the lungs is transported into the blood, so they will try to inhale more, which leads to the flattening of the diaphragm because constant hyperinflation of the lungs and actually reduced efficiency of respiration. Now, air pollution and tobacco smoking. Yes, tobacco smoking is bad. Air pollution, how bad it is? It's pretty bad. In China, some cities, they now start to think about the consequences of fairly non-restrictive policies on the industrial gases, industrial emissions. But some Chinese physicians say that, say, in Shanghai or Beijing, it doesn't really matter if you smoke or not, if you live in the city. The level of pollution is horrendous. So you're going to develop some sort of lung disease sooner or later. Okay. I can tell you from my personal experience, I grew up in what I call Russian Houston, not by size, but it's a Russian space city, basically. So we had all kind of industries that were making rockets and rocket fuel, and you name it. Like the entire space ship and space rocket was assembled in the plants there and shipped to the launch pad. And when I was growing up, everything was very functional. They were building those rockets, working with the rocket fuel, so I grew up as a happy boy with bronchitis because of the air pollution. And then by the end of the 80s, when the Soviet Union started to collapse, all that industry collapsed as well, and the air started to be much better. So my bronchitis went away, basically. So it was noticeable. And our family doctor, she said that she's seen a lot of it. When those plants shut down eventually, kids became healthy. Well, parents lost the job. It's kind of not win-win situation. Now, chronic bronchitis. Chronic inflammation of the respiratory passages. The problem with chronic bronchitis, think about this. What do you have in your bronchi and trachea to get rid of mucus? Cilia. Do they have limited capacity for moving mucus? Of course, they cannot pump like 5 cubic feet of mucus every day. So, if inflammation in the bronchi is permanent, then amount of mucus that is produced, it is far more than cilia can possibly remove. Mucus stays in the bronchi, and instead of working as an effective trap that removes pathogens, it becomes a trap that traps the pathogens in the bronchi, leading to inflammation, infections, all that kind of stuff. That makes sense? There's no cure for chronic obstructive pulmonary disease, only treatments. Anti-inflammatory, bronchodilators, different sympathomimetic agonists of beta-adrenergic receptors, as far as I remember. Oxygen in severe cases. Because if you think about it, in people who suffer from COPD, partial pressure of oxygen in the lungs becomes so low that on the hemoglobin dissociation curve, they're not in this area anymore. They shift to this area. So the amount of oxygen that binds to hemoglobin becomes really low, which leads to hypoxia in tissues. Not enough unloading, right? So they have to take oxygen just to get to this level. Now, anatomically, people have different strength of inspiration and expiration. So people with COPD often define, they divide it into groups of pink puffers, people who are really thin, but they breathe really, really, really well, and they still manage to maintain practically normal concentration of oxygen in the blood. And blue bloaters, people who are more stocky and they respiratory physical capacity to respire is lower, so they do become hypoxic. That's why they're called blue bloaters. They become cyanotic. Now, the example of reversible obstructive pulmonary disease is asthma. There's a trigger. It can be exercise-induced asthma. It can be allergy. Okay, that trigger leads to bronchoconstriction and a decrease in ventilation. Treatment is usually inflammation in the bronchi. Okay, that inflammatory response that constricts the bronchi can be treated by epinephrine bronchodilator. Now, if inflammation happens for an extended period of time, that may lead to accumulation of mucus, and basically just the exudate comes from inflammation. Okay, and that may further obstruct airways. Is asthma dangerous? Yes, very. When we moved to Ohio, still, for me, it's terrible. We got a call from school. It cleared out. Basically, one of my kids' classmates, he was in 5th grade? Yeah, 5th grade. He died in his sleep because of the asthma attack. He was severely asthmatic. So he had basically chronic asthma. He had to carry an inhaler. But he passed away in his sleep. He didn't even wake up because of that sudden attack when he was asleep. So yeah, it can be very, very dangerous. And that's why, you have to watch. I know that in premature babies who, yes?
If people with sleep apnea wake up from the lack of oxygen, why wouldn't that get woken up? Because my brother has chronic asthma, and when he was little, he used to wake up 3 times a night with an asthma attack.
When in sleep apnea, they usually wake up because of the low CO2 levels. Okay? So they have a constriction of the blood vessels, and it's just what's going on. But with asthma, it's basically a suffocation, sudden suffocation.
So it's just too quick for him.
Too quick, yeah. They just don't wake up. Babies with, think about this. So one is asthma. Another condition that is fairly common. It's technically neither obstructive nor somewhat restrictive disease. Babies that were delivered prematurely, as we mentioned before, often have decreased levels of surfactant in the lungs, which may lead to alveolar collapse. Especially, not 2 weeks preterm. I'm talking about 4 months or 3 months preterm. So these babies have to wear, when they sleep, special monitor that will alert parents if saturation, oxygen saturation, hemoglobin saturation falls below critical level. because that can be life-threatening. Why I'm saying it's not, it's hard to say if it's obstructive or restrictive, because technically it's not obstruction of the respiratory passages. It's an ability of alveoli to inflate, okay, which has nothing to do with diameter of bronchi, and technically has nothing to do with irreversible destruction of alveoli. Does that make sense? And it takes a while. So basically for those babies, the vaccines against like influenza or respiratory syncytial virus, they critical. Like, they out of the hospital, like first 2-3 weeks they home, they must be vaccinated. Okay, because respiratory diseases like this can kill them. Now, TB and lung cancer. I could talk. Shameless plug, come to my micro. We'll talk about TB, my ass. Oh yeah, we're going to talk about TB. It's infection. Horrible infection. Very infectious pathogen. Only 5% of people who are infected develop clinical symptoms. Estimates put 2/3 of the world population being infected with Mycobacterium tuberculosis, which is quite a lot. In some countries, it's more than in others. In the United States, levels of infection are much lower. In Africa, India, much higher. In Russia, the majority of people who are infected with TB had some jail time, prison experience. I have a fairly not really funny, more of a sad joke. And if you end up in jail, even for a short period of time, TB becomes sort of a free bonus. You can read about people who were imprisoned and then were freed. They were, people get into the in jail before the trial. Like a trial finds them non guilty. Too late. They come out of the prison. They have TB. It's treatable. The antibiotic course is extremely long. For acute, from 4 months to 12 months, depends on how the patient responds. Here in the United States, if you test positive for TB, even if your chest X-ray is negative, you may still end up taking antibiotics. And in some cases, I know it firsthand, not that I was treated, but a colleague of mine got treated. He didn't have TB. Long story, but he decided to flush them down the toilet. Luck with that, because hospital required regular urine tests to see that he takes those antibiotics. So it's really serious. TB is taken really serious here in the US. Fulminant TB is manifested as the cough, really greeny or bloody sputum, weight loss, people look very anorexic, pale, sometimes even cyanotic. So it's kind of, TB is not very common here. And this radiogram shows different stages of TB in different people. So those shady areas are inflammatory foci in the lungs. TB can travel outside of the lungs and cause systemic disease, but that's kind of beyond the scope. And finally, lung cancer. Did I advertise the cancer book? Did I? No, I did not yet. Yeah. The guy wrote a huge chapter about the origin of lung cancer. It was actually discovered in, how do you call, like in old days, there was a special trade when people were climbing on the roof and cleaned the pipe, the chimneys. Chimney sweepers, yes. So lung cancer was discovered in chimney sweepers. And the guy that discovered it figured out eventually that it was soot that caused it. And then eventually some other doctors noticed that people who smoke have much higher chances to develop lung cancer. And then it was an absolutely epic battle between the tobacco industry and doctors, because tobacco industry was funding unbelievable amount of research that was very skewed, and at that time there was no concept of conflict of interests. Like now, if you publish and you don't put the disclaimer, say, I published the paper that says, I don't know, apples from Sage Farm are awesome. And then if I don't put on that paper the statement that Sage Farm actually pay me for this study, then I'm in a dipshit. And now it's a complete loss of reputation. You do it once, that's why people put, because it's a huge risk. The reward should be astronomical to take risks like that. Because if you end up in science, if you end up with not, without the proper disclaimer, I track it, I keep my eye on all this academic misconduct hearings. Your career is over. No, seriously, it's gone. The problem is, you can be punished. Say you do something wrong, okay? So academic misconduct of some sort, conflict, non-disclaimer of conflict of interest. You keep it under the rug and so on and so forth, and then it's found out. There's a full-blown investigation, and you may lose funding, like federal funding, for, say, 3 years. Somebody says, so what? In 3 years, you will come back on track. No. Because the records, they remain. In internet and all those public records are available. So people look at you and say, this guy or this gal, they committed the fraud. Although the time has gone, this person served the punishment, we're not going to give money because we're not sure. How about personal integrity here? Does that make sense? So it's really, career is over. So people put those disclaimers. But that battle was epic. And eventually it was very, very convincingly demonstrated that smoking leads to lung cancer. Okay. Marlboro Man, you know the story. The guy who was in the Marlboro advertisement died of lung cancer. Yul Brynner. Am I the only person? Yeah. Yul Brynner. The Magnificent Seven. No. Watch the movie. It's a Western. Old Western. Yul Brynner plays the main character. He died of lung cancer and he was smoking like, I don't know, chain smoking basically. Now, you have to understand when we say risk, it doesn't mean that if you are smoking, you're going to die of lung cancer. And it doesn't mean that if you never had a cigarette, you will never have a lung cancer. But your risks are much higher with smoking. Interestingly enough, if you would look at this graph, up to a certain point, the levels of the incidence of lung cancer in males in US was declining, and in females it was going up. I personally attribute it to emancipation. It became more socially acceptable for women to smoke, so they started to smoke more. And then eventually the old health propaganda, in a good sense, made the difference. Now, well, before I mentioned three main cases, types of lung cancer. There was an epidemiological study that looked at the influence. So basically, buying cigarettes here is super expensive. right? I mean, the pack here costs what? It's like $6. And I mean, like, decent, right? Back home, I would say $2. It's like good ones, good. And you can buy crap for like $1. Okay? So no wonder in Russia, the number of people that smoke, we're talking at least 1/3, if not half of the population. Okay? I think Russia is the second in the world in smoking after China. So in the US, that elevated price and public health measures banning smoking from public places definitely did a good job. People started to smoke less, and that reduced the mortality from lung cancer, cardiovascular disease, and so on. However, as the study concluded, that offset in mortality was completely eliminated by the increased mortality due to obesity. So it was like zero-sum game. Now there are 3 major types. Adenocarcinoma, okay, alveoles, glands in the bronchi. Squamous cell carcinoma, specifically in the bronchial epithelium, and small cell carcinoma. Small cell carcinoma, small cell lung cancer is the most severe and most dangerous type of lung cancer. It metastasizes severely, and as in any type of cancer, the key to treatment is the early detection. Okay, so this is the image showing cancer in the lung. Now, the first stage lung cancer is very treatable, either with chemotherapy and/or radiation and surgery. However, 4th stage lung cancer is basically unfortunately, death sentence. Imaging is the key to detection. Again, when I was growing up, even like for kids, we had a mandatory medical checkup every year, which included chest x-ray. Not because I was smoking from the age of 4, but due to the tuberculosis. But a lot of companies, private companies, government companies, they required medical checkup for all personnel every year, which included the chest x-ray, which allowed often to detect lung cancer fairly early. Now, therapies. Growth factor inhibitors. So basically what they try to do, they try to inhibit the growth of a tumor by inhibiting the growth of the blood vessels. Basically depriving the tumor from the blood flow. Yeah, it works, yeah, not so well. Cancer vaccines basically failed because cancers are very different immunologically. Gene therapy, huge failure. One of the best things that was developed in the recent years, you may have seen the ads, the TV, magazines, Opdivo. Have you seen that? It's the PD-1 inhibitor, don't remember. Something related to death. So basically what happens, when cancer develops, when tumor develops, cancer cells manage to produce a molecule on their surface which makes them unnoticed by your T cells. Does that make sense here? So T cell comes by, looks at the cancer cell, which is supposed to look different, right? It's supposed to look different. It's supposed to present a different antigen on its surface. Okay? But your immune system looks at the cancer and says, looks at the MHC class 1, and then looks at this PD-1 molecule. And PD-1 molecule sends the signal, no worries, I'm okay. And the immune system says, yeah, that's fine. We'll just move on. Now, when this mechanism that allowed, when this PD-1 mediated immune evasion was discovered, inhibitor of PD-1 now basically targets, unmasks cancer for the immune system. Does that make sense? It's pretty cool. Yes?
Is that the same molecule as rhesus conflict?
Huh?
Is that the same molecule as the rhesus conflict?
No, it's a different one. It's a different rhesus. It's a D-antigen on the red blood cells. This one is just very, very specific molecular immunological marker. That was a huge deal, really. It was an enormous deal. And one more thing, and I think it's just another brilliant story. Now that I'm not going to ask on the exam, obviously, but just to give you an idea. So that Opdivo treatment, the only not the only downside. First of all, it can be used in a stage 4. It's not going to cure, but it's going to extend survival. So basically, they're talking about 4 times longer. Say, instead of 6 months, 2 years, which is good. Another therapy, not for the lung cancer, just popped in my mind. I'll just tell you because it's so awesome. Therapy for B-cell leukemia. So what scientists do, they take your T cells and they reprogram them to attack your B cells. There's a way to do that. I don't remember if there's some, either they kind of de-differentiate them, program them, and differentiate them. Like there's some fairly routine method to reprogram your own T cells. And then they put those T cells back in you. And your T cells start to attack your B cells. They destroy them all. They do destroy normal B cells, but they also destroy all leukemic B cells. So you have to survive without B cells, which is doable. I mean, you're going to be immunocompromised, but it's doable. At least you don't have cancer. This treatment was initially approved in adults. About a year ago, even less, it was approved in kids. And it's incredibly hard to treat. The B-cell leukemia is hard to treat. The only downsides to those treatments, Opdivo treatment, a year course, is $130,000. It's for lung cancer. The B-cell leukemia treatment for Opdivo, I mean, the monthly bill is about $15,000. So it depends on how many months you get treated. For that B-cell leukemia treatment that I told you about, they don't count in years, they count in rounds. 1 round of treatment is $450. Not dollars. Don't take me wrong. $450,000 for 1 round of treatment. It's a long-lasting, though. It may last for years, but it's still a lot. Okay, it's just, and the main reason, a lot of litigation costs. God forbid something goes wrong, and research and development, because this approach wasn't developed since basically 90s. The amount of money that pharma spent on the research is enormous. Now, regarding the development, now, I'm going to ask basically one thing, if I will ask you. Do we use lungs when we are in the placenta? No. They're filled with fluid. What do we breathe through? Breathe. Like, breathe, quote unquote. Huh? Placenta, yeah. Gas exchange through the placental structures. Yeah, that's it. So I'm not asking about all those developmental stages. Now, it takes some time for the lungs to become fully functional. Basically about a couple of weeks. Okay. And then breathing rate decreases as we grow older. As we become like really, really old, there are anatomical changes that affect the respiratory efficiency. Chest wall becomes more stiff because of ossification of the cartilages. Mucus starts to accumulate in the respiratory passages. So basically, in elderly, pneumonia is a life-threatening condition. Lung elasticity decreases due to various inflammatory processes, fibrosis, and so on and so forth. Alveoli become enlarged, and what we just discussed, they become bigger, so the gas exchange actually becomes less efficient. Make sense? And on top of that, you know how sometimes older people, they have kyphosis? They look like that. That immediately decreases lung compliance, decreases pulmonary ventilation, and makes lungs more prone to infections. So basically, again, what is the preventative measure? Exercise. Because your posture depends largely on the strength of your core and back muscles. Okay? So, the most common disease that is genetically defined in the United States, lethal disease, cystic fibrosis. The disease that is caused by mutation in basically one gene. Gene normally should allow chloride ions to move through the membrane. Okay. Now, if the gene is dysfunctional and chloride accumulates on one side of the cell, inside of the epithelial cells, in mucus accumulates on the other. That abnormal mucus accumulation basically manifests as the obstructive pulmonary disease. And on top of that, you see those green patches here? These green patches represent the infections. Because bacteria, instead of being trapped in the mucus and subsequently expelled, remain in the mucus, start to reproduce, cause the disease. Usually pneumonias and basically chronic bronchitis. Other organs that are affected by cystic fibrosis include reproductive ducts, and especially pancreatic duct becomes basically clogged with mucus and prevents normal release of pancreatic juice into the duodenum. Now, it's ultimately lethal, fairly early lethal. I think the best prognosis is late 20s, maybe early 30s. What can we do? Realistically, what is done now? Drugs that the mucus thinners, okay, chest percussion, special techniques that basically, tapping on the chest to loosen the mucus so it can be expelled easier. Inhalation of the saline to also loosen mucus. That's what's done. I'll get to antibiotics in a minute. There are ideas to, introducing the artificial chloride channel, introducing, replacing defective gene with normal gene. There are multiple approaches. What we can hope for is that there will be some very wise person who will figure out how to regulate the CRISPR technology that can be applied to the babies. CRISPR-Cas9 technology, if you've never heard about it, read about it. Basically, in a nutshell, it's the genetic approach that allows you to manipulate human genes like Lego. You can cut a gene, and replace it with some other gene. And it's very easy to do now. It has very high accuracy, very low, basically zero error rate now. There's a guy in Oregon Health Sciences University that showed it, developed the method how to do it basically without any errors. It's pretty awesome. Of course, the only problem is that, we can have now babies a la carte. Like, I want a baby with, blue eyes, and that's it. My genetic fantasy, I'm lost at this point. But whatever. Think about it, okay? I don't know. But it also gives us a tool to fix genetic diseases like this and the embryonic level. So, if there will be a person who will be able to regulate it, that would be awesome. Seriously. So far, the CRISPR-Cas9 modification babies is banned in all countries that can do it, except one. No? 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 China. Because they don't really have to. If they will decide to do it, they will just do it. So just didn't move that. They moved pretty far, but they kind of getting there. Okay. So maybe someday they will be able to treat it. Okay. We're going to take a break now, and when we'll come back, review